Okay, so we have just a few other things to talk about. I want to talk about blocking and that aspect of experimental design. Okay, as part of So oftentimes you'll have a situation where the you're interested in the effect of one categorical variable on the response, okay? But there might also be just a known other variable. There might be another variable that you know affects the response as well. And so here you are, and maybe for whatever reason you can't eliminate this other variable. Okay, so this variable just kind of exists, and you also know that it affects the response, and so you want to account for this in your experimental design and also in the analysis. Okay, so let's say you have I don't know, a room where you're going to be growing plants here, okay? And so let's say there's a window here, okay? And the room is kind of set up where just as the day goes by, we can kind of separate our room into kind of these different zones here, and the idea being, oops, here there's lots of sun, we'll say lots of sun. This will be little sun and some sun. Okay. And let's say you wanted to I don't know, just test out different fertilizers or something, okay? And you see you've got the control group. And then you have maybe fertilizer 1, and you have fertilizer 2. Okay, so a very bad design let's say you have 6 plants of each. Okay, so we want to produce replicates here. So a very bad design would be to put all 6 plants of fertilizer 2 in the lots of sun. Okay. Okay, and then all 6 fertilizer 1 go in some sun. And then all 6 control go into little sun. Okay? Because at the end of the experiment, if we detect differences, okay, any differences detected between the 3 fertilizers or the 3 treatments, okay, any the differences between the treatments cannot be distinguished from the differences between sunlight. Okay, so at the end of the experiment, any differences that exist between treatments cannot be distinguished from the differences in sunlight. Okay, and so because of that, this would be a very bad design, right? Because if let's say all the plants in fertilizer 2 grow the most. Is it because fertilizer 2 is super effective, or is it just because they got lots of sunlight? We don't know. So that's bad, okay? We can go for a completely random. With a completely random design, we just say, oh, okay, we've got 18 plants. Let's just randomly assign 6 to fertilizer 2, randomly assign 6 to fertilizer 1, and randomly assign 6 to the control, and we'll throw them into our room, okay? And so, you know, because of this, we'll also just randomly assign some to lots of sun, some go randomly to some sun, and some go randomly to little sun. And with a completely randomized design, this helps, but it's also possible that because it is completely random, it is possible that 4 fertilizer 2 plants go into lots of sun, and only 1 fertilizer 1 and only 1 control go into lots of sun. Okay, you can still get kind of this uneven balance if it's completely random. Okay, so still possible to get, quote, uneven balance. Okay, now we're hoping that the randomization helps avoid this, but because it's random, it might not. Okay, so you know, we could get, you know, 4 of fertilizer 2 in lots of sun. Okay, and then so at the end, if fertilizer 2's average is higher than the rest, we don't know if it's because a lot of these plants ended up in the lots of sun zone. Okay, and so we have the randomized block design. That says, hey, we want to know the difference between these different treatment groups. We know sunlight has an effect on plant growth. We know that this is a known phenomenon. Okay, we're not interested. The question we're asking isn't, does sunlight affect plants? We know that this is true. And so what we're going to do is we're going to create blocks and say, you know, the lots of sun block, we're going to make sure we get 2 from each of the 3 treatments. In the some sun, we're going to make sure we get 2 from each of the 3 treatments. And in the control group, in the little sun, we're going to make sure we get 2 from each treatment. Okay, so we say lots of sun, you know, we kind of force 2 plants from each treatment. Okay, you know, and then, you know, so some sun, the same thing, and little sun. Okay, we make sure we get 2 from each treatment, 2 from each treatment. Okay, and then this way we can kind of do better analysis here. So maybe what we see is, you know, all 6 plants in the lots of sun grew a lot. This is expected. and then the 6 plants in the little sun grew very little. But what we might see is that across the board, fertilizer 1 grew, the 2 plants from fertilizer 1 grew the most in the lots of sun area, and when we look at the some sun area, fertilizer 1 grew the most, and in the little sun area, fertilizer 1 also grew the most if we control for those things, okay? And you want to make sure you have more than one replicate from each thing. So if we only had 3 control group plants and 3 fertilizer 1 and 3 fertilizer 2 group plants, this would not be a good analysis, because we would run out of what we call degrees. We would run out of degrees of freedom, or what we would have is we would just have one plant with fertilizer 1 in the lots of sun area and one plant from fertilizer 1 in the some sun area. And you don't know if the plant that grew if that plant happened to grow the most, you don't know if it's a fluke, like just this plant was extraordinarily unusual, or if it's the effect of the sun or the fertilizer, okay? But by making sure you have more than one in with each treatment and each block, you can account for the variation. So if both of the plants under fertilizer 1 grew the most compared to the others in the lots of sun area, that's evidence that fertilizer 1 is effective. And if it's the same across the board for all 3 zones of sunlight, and fertilizer 1, both plants on fertilizer 1 grew the most across all 3 sunlight zones, then fertilizer 1 is effective. You'd have strong evidence for that. Okay? So, so this is the idea behind blocking in experimental design. Is that all right? And then, so if you take a class on experimental design, you will talk very thoroughly about this this concept of blocking. This is just kind of like the 10-minute exposure to this, and it's a very simple example. But we can imagine experiments being much more complicated and things like that. And just in reading the research article about ADHD and St. John's wort, there's a lot of thought goes into how do we assign these treatments and things like that. So that should be covered in a good experimental design course. So a lot of these things that you've got to think about, just because you don't want, at the end, if you find results that this group is different from this group, you don't want it to be like, oh, I forgot to account for this thing, and the random assignment happened to assign a whole bunch of whatever this thing into this group, and so something like that. So it could be argued that boys are different from girls with respect to whatever thing that you're looking at, and if you just did a completely random assignment, it could be that group 1 happened to be a lot more boys and group 2 happened to be a lot more girls, and if you discover differences between the 2 groups, you might not be able to distinguish that from, is it the fact that there were different sex ratios in the 2 groups, or are the 2 treatments effective, or different in effectiveness? We don't know. So these are just things you've got to account for. Okay, and as far as the analysis goes, okay, we have ANOVA for block design. Okay, and so I will just kind of briefly talk about these. We're not going to necessarily get into all of the nitty-gritty, but the idea here is that the model is that your data point y sub I is going to be the result of the grand mean plus the treatment effect. Okay, so this is treatment effect, whether you're on diet 1, diet 2, or diet 3, or whatever it is, fertilizer 1 or the control. and then you have a block effect, and then you've got the residual. Okay, and then your ANOVA table will have the source will be treatment, blocks, residuals, and then you've got total. Okay, and then you'll have the other columns: degrees of freedom, sum of squares, and all of these things. Okay, and effectively these are, you look at the difference between the grand mean and the mean of each treatment, and this would be the difference between the grand mean and the mean of each block, so on and so forth, and then the residual difference. Okay, so I guess you would have the null hypothesis for treatments would be that, you know, tau 1, tau 2 is equal to all of these, all equal to 0, and then there is also a null hypothesis for blocks, block 1, block 2, all of these equal to 0, and the alternative is at least 1 is not 0. Okay, so that is the block design. And so you'd have an F for each row, treatment and blocks, but not residuals. Okay. Okay. So that is ANOVA for a block design. And then we have a two-way ANOVA, which is similar, but takes into account the interactions between our factors, okay, or our treatments.
Question.
Yeah.
Once you get to the F statistic,
Yes.
the last column,
Yeah.
what would you be using for your numerator and denominator?
Yeah. Okay. So, this would be total number of ones. This will be number of treatments minus 1. This is number of blocks minus 1. And this would be whatever the difference, so it adds up. I wasn't going to go through all of this. Okay, then so we have sum of squares treatment, sum of squares blocks, and then we have sum of squares residuals. And then this is going to be sum of squares divided by degrees of freedom, sum of squares divided by degrees of freedom. Oh, I'm sorry. And then, yeah, we also have sum of squares divided by degrees of freedom here. So I'm skipping all the formulas. And then, so this would be mean squares of treatment divided by mean squares residual. And this would be mean squares blocks divided by mean squares residual. So in these final F statistics, the F that we have here, the numerator is the degrees of freedom for number of blocks minus 1 divided by degrees of freedom for the residuals. So whatever it is, so that this adds up. So these plus all three of these add up to the total. Okay. Good. And so that's all of the ANOVA tables. Okay. Let's talk about two-way ANOVA, which is very similar, okay? Two-way ANOVA. And so here we have two variables, okay? So we have two factors. And we're interested in the effect of each factor. And we're also interested in what's called an interaction effect. Okay? Okay, and so so our design here is that the data points is equal to the mean plus the effect of the treatment plus the effect of the block plus an interaction between not the block, I guess treatment 1 and treatment 2. So this is treatment 1 effect, treatment 1, and this is treatment 2, and this is the interaction between the treatments. And this would be the residual. So the idea here is perhaps, you know, maybe if you did a separate study, you learn that treatment 1, whatever it is, produces some kind of effect, okay? So maybe it's like, what's going to help, I don't know. I can't think of something. You know, what helps students perform well on a math exam, okay? So maybe we want to know, you know, performance on math exam. Okay. All right, and then so maybe in a separate study, treatment 1 is they attend you know, some class, okay? So treatment 1 is they go to you know, math class, special math class. So this is treatment 1. Okay, and then so maybe you studied this by itself, and the difference that special math class produces is it improved students' scores by 5 points or something like that. Okay, and it's statistically significant, but you know, it improved their scores by 5 points. Okay, and then maybe treatment 2 is they got calculator training or something like that. Or maybe they got a special calculator that helps them out, okay? And then treatment 2 by itself, when studied, maybe they did another study, that helped students' scores improve by 3 points. It was statistically significant. On the average score improvement was 3 points. So you might expect that if you combine the special math class and the calculator training, you would expect an improvement of 8 points total or something like that. But there could be some kind of, I don't know, magical synergy that happens with the special math class and the calculator training combined, that instead of producing a total of 8 points, maybe it produces an increase of 12 points or something. Okay? And if that's the case, then there is what we call an interaction that produces, that basically says the net effect of treatment 1 and treatment 2 cannot be explained just by treatment 1 and treatment 2 alone, but rather there's something, some kind of what we call an interaction that says maybe when they work together, they produce more than what they would have by themselves. Okay, so maybe this is like plus 5, here's plus 3, but then there's an interaction that says, you know, somehow when combined, the effect is, you know, more or less than what we would have expected by just kind of simply adding these together. Okay, and then so we account for that by just throwing in this third term, the interaction term. So maybe this is a +4 or something, okay? Which means this is pretty big, right? Because the calculator in of itself, maybe, you know, +3 is statistically significant, and you know, I don't know, maybe the school district is willing to spend lots of money getting calculators for this thing and spending money on the special math class. But they should say, well, if you're going to bother with this, go all the way, because you're going to get even more fruit. Or maybe it turns out that this is negative, that math class by itself is +5 and calculator is +3, but then when you combine the two, you're expecting a total of +8, but you're only getting +6. Maybe, I don't know, maybe there's a limit to how much students can improve or something. You know, who knows, okay? So that exists, and then basically for the ANOVA table, you just added another line in there that just says there's another source of variation, and that's the interaction, okay? I want to, I'm going to talk briefly. You have another short lab. It's non-R related, and I have to get this copied over here. Okay, well actually, I guess I got rid of it last quarter also. Okay, so maybe we're only going to have 3 labs here this quarter. But, well, I wanted to just kind of demo how, oh, sorry for all of this, how simple R makes the analysis of ANOVA data. Okay, so I'm going to just type in our data here. This is our lamb weight data, and you don't have to do it this way. You could import it from a Excel table, okay? So basically I'm just saying I'm assigning each of these to so I'm taking our measurements X and my measurements Y, and I'm going to put them together, and this will be our data. Okay, I'll call this data. Oh, I'm sorry, not cbind. I gotta call this data.frame. Did I do something wrong? AAA 1, 2, 3, 4, 5. Oh, there's one more C that I left off. Okay, so when we look at our data, it's it just kind of lists off all 12 measurements that we have, and the Y is our 3 groups, right? Group 1, Group A, Group B, and Group C. Okay. I purposely used letters rather than numbers, because if I used numbers, R would think this is a numeric variable. It would think the third group, that it would think we're measuring something, and that the third group has 3 times as much whatever it is than Group 1, okay? Which is not the case. These are just Group 1, Group 2, and Group 3, but it's not that Group 3 has 3 times more whatever than group 1 does, or group 2 doesn't have twice as much as whatever group 1 is. So here, if I use letters, R knows these are just labels. There is an option. You can say treat this as a factor, which R will then say, okay, I'm going to ignore the numeric value of these things and treat it as a factor. Okay? So we do something called AOV for ANOVA, and we just say explain X by the different groups. Okay? So you just put a little squiggle there, and it says it's done. Okay? And then you can just ask for the summary of this. X as explained by Y. And this produces the exact what is it? The ANOVA table that we created in class, right? So if you look in your notes, the values that we have here are exactly what we have. We have 2 degrees of freedom due to Y, our groups. We have 9 degrees of freedom from our residuals, sum of squares, the mean squares. It calculates our F statistic, and it throws it into the p-value, calculates the p-value for us, and it says your p-value is 0.491. Okay, and so so ANOVA, so R makes it very easy to perform ANOVA. If we had another, like another factor, okay, so if I had another data set, and if we wanted to do kind of this block, a block design, like we have, you would just say X as explained by Y plus whatever the block is, okay? And if you wanted the interaction, you would do a star to say I want the effect due to Y and the effect of the block and their interaction. But you can just do Y plus this, and this will be the command for that. And then you just say, oh, I want the summary. I want to see the table, and you do that. So I won't make you guys do this as part of your lab or homework, but I do want to I just wanted to show you that, like, some of this stuff, you know, like, it took us a long time just to get these numbers. It's very easy to do it with R. Okay. Are there any questions? Okay, we'll end there then, and we'll see you guys not next week, but in 2 weeks. Okay.
So we have the quiz and the lab that session?
No, I guess we'll just have 3 labs. I've cut out, I guess, our labs here. So.
But there will be the quiz, though, right?
There will be a quiz in 2 weeks. Yes. So enjoy your Thanksgiving, and we'll see you guys in a couple weeks.